The universe is a silent ocean of darkness, but sometimes something whispers. From the infinite void between stars, mysterious travelers are now crossing into our solar system. These are interstellar comets, icy nomads from other suns, and they are not silent. They carry with them cryptic signals, whispers of light, radio waves, and gravity that defy all our expectations. By the end of this journey, you will know the 25 most baffling signals these cosmic messengers have sent our way, each one a puzzle waiting to be solved. What strange acceleration made one object seem almost artificial? Why did a comet from another star leave a chemical signature found nowhere on Earth? We are about to dive into a new frontier of astronomy where every flicker of light might be a message. What do you believe is waiting for us in the dark? Our story begins not with a roar, but with a silent, dark streak against the stars. In October 2017, astronomers in Hawaii spotted a visitor moving too fast to be from our own solar system. It was the first of its kind ever seen, a messenger from another star. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was no ordinary comet. It had no visible tail of gas and dust, the classic signature of a melting ice ball. Its shape, inferred from how its brightness changed, was wildly elongated, like a cosmic cigar tumbling through space. But the real mystery was how it moved. As it sped away from the sun, something gave it an extra push. Its trajectory could not be explained by gravity alone. This non-gravitational acceleration was subtle but undeniable. The most natural explanation was outgassing, like a rocket engine where hidden jets of vaporizing ice propel an object forward. Yet no telescope could detect any gas or dust around Oumuamua. It was accelerating in total silence. This void of evidence became the first signal, a blank space on our sensors that screamed with questions. What unseen force was at work? The scientific community scrambled. Some proposed exotic ideas, like it being a chunk of solid hydrogen ice evaporating invisibly. Others, including a few prominent astronomers, dared to voice a more staggering possibility. Could this acceleration be artificial? Could Oumuamua be a light sail, a piece of ancient technology from a distant civilization, using the pressure of sunlight itself to navigate the galaxy? The hypothesis sent a shockwave through the world of astronomy and beyond. In response, projects like Breakthrough Listen aimed the Green Bank telescope at the retreating object. They scanned across billions of radio channels, listening for any hint of a transmitter, any whisper of technology. They monitored specific frequency bands, those quiet windows in the cosmic radio noise where an intelligent signal might logically be placed. The result was a profound and absolute silence. Not a single artificial pulse was heard. This silence, however, was not the end of the mystery. It deepened it. The lack of a radio signal did not rule out an artificial origin. It merely ruled out an active, broadcasting one. A derelict probe, long dead, would be just as silent. So we were left with an enduring puzzle, our first entry in the catalogue of cosmic whispers. A strangely shaped object accelerating by means unknown, leaving behind only the echo of our own unanswered questions. That silent departure taught us a crucial lesson. Sometimes the most compelling signal from the depths of space is not what we hear, but what we cannot explain. Oumuamua's silent departure left astronomers staring into the dark, wondering if its strangeness was a fluke. Then, just 2 years later, the cosmos sent a second messenger. This one arrived with a brilliant classic cometary tail, a familiar sight against the starry backdrop. Discovered by amateur astronomer Comet Borisov, this visitor was named Comet 2I/Borisov. At first glance, it seemed almost ordinary, a textbook dirty snowball from another star. But as it swung around the sun, the most powerful radio telescope array on Earth, known as the Atacama Large Millimeter Array or OLMA, turned its immense dishes toward it. What they detected was a whisper, a faint but incredibly revealing signal. Oumuamua listens in millimeter waves, a type of light that can pierce through the dusty coma of a comet to sense the chemical fingerprint of the gases within. The signal from Borisov told a clear story. It was rich in carbon monoxide gas, far more than any comet from our own solar neighborhood. This was a pristine relic, a cosmic time capsule that had formed in the extreme cold of another star's distant reaches and had never been warmed by a sun until now. Its very normalcy as a comet, however, created a new and different kind of puzzle. Teams across the globe, just as they had with Oumuamua, scanned Borisov for any sign of artificial radio transmissions. They listened intently across the same quiet bands of the spectrum, and once again they heard nothing. No structured pulses, no carrier waves, no technosignatures. But this profound silence meant something else entirely. With Oumuamua, the lack of a radio signal was set against a backdrop of bizarre physical behavior. With Borisov, the silence was set against a backdrop of perfect cosmic normality. This forced a crucial shift in perspective. It meant that the absence of a signal could be a signal in itself. If an interstellar object behaves exactly as natural astrophysics predicts and still shows no signs of technology, what does that tell us? It tells us that perhaps the universe is simply full of natural icy wanderers, and that the extraordinary weirdness of Oumuamua might be the rare exception. Or, more intriguingly, it tells us that if intelligence does send probes, they might be engineered to be utterly silent, or to mimic natural phenomena so perfectly that they hide in plain sight. Borisov's whisper was not a shout of alien technology, but a quiet lesson in cosmic statistics and the art of camouflage. Two silent messengers taught us to listen to the void. But a third signal arrives from a system still in its cosmic infancy, a place where planets are being born. Around a young star named SETI, astronomers found something extraordinary, a giant planet several times the mass of Jupiter orbiting incredibly close. They called it SETI b. This planet alone is a marvel, but the star it circles began to whisper secrets of its own. Observers noticed its light would dip, not in the clean, periodic way of a planet passing by, but in erratic, dramatic bursts. These were not single shadows, but complex patterns of dimming that suggested something vast and fragmented was crossing between the star and us. The leading theory paints a staggering picture. It proposes that SETI b's immense gravity has stirred up a vast cloud of primordial debris, a sprawling family of countless comets and icy bodies. As these objects swing close to their furious young star, they vaporize, creating enormous, swirling clouds of gas and dust that blot out the starlight. This is a natural, if violent, nursery story, yet the patterns give some researchers pause. Could the dimming be too structured, too regular in its irregularity? This is where a more speculative idea emerges from the shadows of hypothesis. What if those shadows are not from natural clouds, but from something built? The concept of a Dyson swarm, a vast collection of energy capturing satellites orbiting a star, could theoretically cause similar complex dimming patterns. In the SETI system, the idea seems almost science fiction, a megastructure around a star so young that life, let alone a star-spanning civilization, should have had no time to evolve. The debate, therefore, is not about proof, but about imagination's limits. Are we seeing the chaotic, beautiful violence of a solar system being born, where a giant planet shreds comets by the thousands? Or does the very strangeness of the signal compel us to consider every possibility, no matter how remote? SETI b's enigma forces a question that will echo through our entire list. Where do we draw the line between an unprecedented natural phenomenon and a signature of intelligence? Sometimes the universe shows us its construction sites, and we must decide if we're looking at a cosmic accident or the first traces of a blueprint. Deep in the heart of our own galaxy, another type of whisper cuts through the static. These are not the silent accelerations of dark visitors, but sudden, deafening shouts of pure energy. Astronomers call them fast radio bursts, or FRB. For a few thousandths of a second, these events release more energy than our Sun does in 80 years. Most come from galaxies far, far away, but two specific bursts have turned attention to our own cosmic backyard, toward the supermassive black hole at the Milky Way's center, a region known as Sagittarius A star. The first of these bursts was captured by the Parkes radio telescope in Australia. It was incredibly brief, a single spike of radio waves, but its fingerprint was odd. Every radio burst traveling through space gets stretched out, an effect called dispersion. The amount of stretching tells you how much material it has traveled through. This burst's dispersion measure was too high for a source within our galaxy, according to conventional models, yet its direction pointed straight toward our galactic core. Then, years later, the CHIME telescope in Canada detected another. This one was a repeater, sending out multiple brilliant pulses in quick succession. Its energy profile was bizarre, with a structure that seemed to rule out the usual suspects like neutron stars. Both signals, separated by time and telescopes, seemed to originate from the same ominous direction. So what could possibly create such monstrous, localized blasts of radio noise in the violent neighborhood of a supermassive black hole? One compelling theory points not to stars or black holes themselves, but to a vast, unseen swarm of icy bodies. Imagine a cloud of trillions of interstellar comets drawn in and trapped by the immense gravity of Sagittarius A star. In that chaotic, high-speed environment, collisions would not be gentle. Comets would shatter, icy fragments would vaporize in an instant, magnetic fields, twisted and amplified by the black hole's influence, could turn these hyper-energetic collisions into natural particle accelerators, focusing the energy into focused beams of radio light that flash toward Earth. It is a natural explanation, but an extreme one, requiring a population of objects we have never directly observed. These dual bursts from the galactic center force us to confront a new possibility. The most mysterious signals in the cosmos might not always come from the distant void. They could be erupting from the very heart of our own home, generated by a hidden storm of icy nomads caught in a gravitational maelstrom. The galactic center's violent bursts are one extreme, but some whispers from the dark are far more subtle and patient. Deep in the radio quiet of West Virginia, the giant dish of the Green Bank telescope has been listening to a different kind of mystery. Over several observing sessions, it has picked up a series of faint, repeating radio echoes. These are not the millisecond shouts of a fast radio burst, but softer, more drawn-out pulses that come and go on a schedule that seems almost but not quite random. The most baffling part is their apparent origin point. By tracing their path backward, astronomers found they seem to emanate from a patch of empty space where nothing visible resides. The leading hypothesis points to a theorized class of object called a dark comet. Imagine an interstellar wanderer so old, so depleted of the volatile ices that create a bright glowing coma, that it is essentially a mountain of dark, porous rock and carbon-rich dust. To our optical telescopes, it is virtually invisible, a ghost in the void. Detecting such a stealthy object is one of astronomy's greatest challenges. It does not reflect enough sunlight to see, and with no outgassing, it leaves no chemical signature to sniff out. We might only notice it if it passes directly in front of a distant star, or if, by some mechanism, it chooses to speak. This is where the radio echoes offer a tantalizing clue. A dark comet, though inert on the surface, is still moving at tremendous speed through the sea of particles and magnetic fields that fill interstellar space. One compelling idea suggests that as this dark nucleus plows through the thin gas of the interstellar medium, or as it encounters the magnetic field of our own solar system, something extraordinary happens. Charged particles from the solar wind could bombard its surface, not causing it to glow, but exciting subtle electrical currents within its dusty, conductive crust. Alternatively, the comet's own weak magnetic field, if it has one frozen within, could interact with the galactic magnetic field, creating sporadic bursts of radio emission. These would not be the smooth, constant radio glow of a normal comet's ionized gas tail. They would be crackling, unpredictable pulses, their structure dictated by the comet's chaotic rotation, the unevenness of its surface, and the shifting winds of space itself. To our algorithms, these sporadic pulses could easily sound coded, simply because they do not match any clean, natural emission model we have on file. They are the static hiss of a dark rock tumbling through a magnetic sea, a whisper so faint we can only hear it when the universe is perfectly quiet, and we are listening very, very carefully. This signal forces us to ask if the most common interstellar travelers are not the brilliant, icy comets, but these silent, dark ghosts, and that their whispers are the true background noise of the galaxy. The whispers from dark comets are faint and sporadic, but history holds a record of one signal so powerful and strange it was almost declared a message. In the late 1980s, a team of astronomers using a radio telescope in the Soviet Union detected something astonishing. It was a strong, narrowband radio signal, a focused beam of energy that seemed to originate from the direction of the star Vega. This was not random static. It pulsed with a specific frequency, and for a brief, electrifying window, it matched almost perfectly what scientists predicted an intentional beacon from an advanced civilization might look like. The news sent a tremor of excitement through the global scientific community. Had we finally heard the call, the signal, however, was maddeningly transient. It appeared, and then it vanished, never to be heard again despite years of dedicated listening. For decades, the Vega anomaly remained a tantalizing enigma, a ghost in the machine of the search for extraterrestrial intelligence. But modern astronomy offers a new, breathtakingly natural interpretation that ties it directly to our interstellar wanderers. Imagine not a single transmitter, but a vast, drifting cloud of countless icy bodies, a primordial swarm of interstellar comets passing through the Vega system. As these frozen objects are warmed by the star's light, they release plumes of gas and dust. This material becomes ionized, charged by stellar radiation. In the complex magnetic environment around a star, these ionized clouds can act like natural amplifiers and reflectors for background radio noise. They could focus and modulate the star's own radio emissions, or even emissions from deeper space, creating a temporary, lens-like effect that produces a strong, narrowband signal directed right at Earth. The signal's duration, a matter of minutes or hours, perfectly matches the transit time of such a swarm passing through our precise line of sight. Its compelling structure, which seemed so artificial, could simply be the signature of a natural cosmic interferometer, a chance alignment of trillions of tiny mirrors made of ice and plasma. This explanation does not rob the Vega anomaly of its mystery. It transforms it. It suggests that the universe itself can mimic intelligence on a staggering scale, using nothing more than ice, dust, and the laws of physics. The signal we once thought might be a greeting could instead be the echo of a silent, frozen migration, a reminder that nature's palette is vast enough to paint pictures we mistake for purpose. The galaxy's grand whispers and ghostly echoes set the stage for a far more subtle kind of detection. Far from the radio noise and visible light, in the quiet, long wavelengths of the infrared spectrum, the Spitzer Space Telescope once listened for the faint warmth of the cosmos. Its sensitive instruments picked up something curious around 3 separate star systems, all within the Triangulum constellation. Each star showed a faint, persistent infrared excess, a gentle glow of heat that could not be explained by the star itself. This was not the bright, warm signature of a typical debris disk, the kind of close-in, dusty ring where rocky planets form. Those disks are like a cloud of fine flour close to an oven's light. The Triangulum Trio's signal was different. It was a diffuse, cold whisper, the kind of heat you'd expect from something very dark, very distant, and very, very still. The best fit for this faint thermal signal is a vast, sparse cloud of countless cold cometary nuclei. Picture not a brilliant, active comet with a tail, but the dormant, frozen heart of a comet, a dark iceberg in space. Millions of these objects, orbiting far from their host star in a deep freeze, would absorb just a tiny bit of stellar warmth and re-radiate it as this faint infrared glow. This discovery presents a beautiful cosmic puzzle. Are we looking at the native Oort clouds of these stars? Every star is thought to be born with a distant shell of icy leftovers, a cosmic attic full of frozen history. If so, the Triangulum Trio gives us a rare peek into the architecture of other solar systems, confirming a universal blueprint. But there is another, more thrilling possibility. What if these are not native clouds at all? What if we are seeing captured clusters of interstellar comets, vast swarms of nomadic ice that were gravitationally trapped by these stars as they passed through the galaxy? Each faint infrared glow would then be the thermal signal of a captured population, a family of travelers from different cosmic origins now sharing a common home. This subtle warmth is their only collective voice, a whisper that says, "We are here, we are many, and we come from elsewhere." It is a signal that blurs the line between what belongs to a star and what is merely passing through, reminding us that a star's gravitational reach can create a museum of frozen visitors from all across the galaxy. The faint infrared warmth of distant comet clouds is a patient collective signal, but sometimes the universe delivers a message that is sharp, singular, and impossible to ignore. Deep in the archives of the Chandra X-ray Observatory lies a data point so precise and so fleeting it feels almost intentional. It is known simply as the pulsar blip. Chandra was monitoring a known pulsar, the rapidly spinning corpse of a massive star. This object acts like a cosmic lighthouse, sweeping a beam of intense radiation across space with metronomic regularity. Astronomers can predict its pulses down to the millisecond. During one observation, the telescope recorded something extraordinary. Amid the steady heartbeat of the pulsar, there was a single, massive spike in X-ray intensity. It was a flash hundreds of times brighter than the pulsar's normal output, and it lasted for less than a second. This alone would be strange, but the timing was what sealed the mystery. That powerful blip coincided perfectly with the predicted passage of a theorized interstellar comet through that exact region of space. No comet was directly seen, but its trajectory had been inferred from subtle gravitational tugs on other objects. So what could have happened? The leading theory is a spectacular cosmic interaction. Imagine this dark, icy wanderer, surrounded by a thin halo of gas and dust, its coma, slipping silently through the void. Its path takes it directly through the pulsar's devastating lighthouse beam. For a fraction of a second, the comet's coma is flooded with the pulsar's immense energy. The gas and dust in that halo become supercharged, absorbing that energy and re-emitting it in a furious, amplified burst of X-rays. It would be like a tiny speck of fog suddenly flashing into brilliance as a searchlight sweeps over it. Then the comet moves on, the beam passes, and the signal vanishes forever. The odds of such a perfect alignment are astronomically low. It requires a pulsar's beam, which is incredibly narrow, to intersect with a comet's diffuse coma at the precise moment our most powerful X-ray eye is watching. This one-time event has never been seen again despite constant monitoring. That makes the pulsar blip a unique specimen in our catalog. It is not a pattern to be studied, but a single, perfect data point. It is the universe offering one definitive snapshot of a hidden traveler, illuminated not by sunlight, but by the focused beam of a dead star. We are left to wonder if it was a miraculous stroke of observational luck, or if such interactions are common in the galaxy's dark, and we have simply learned how to listen for the flash. A galaxy cluster millions of light years away once seemed to speak with a voice from our own backyard. During a deep radio survey of the Hydra cluster, a distant gathering of galaxies, astronomers detected a bizarre anomaly. It was a brief, broadband radio glitch, a burst of static across many frequencies. The signal's properties were unmistakable. Its dispersion signature indicated it originated from within our solar system, likely from Earth's own ionosphere. Yet, when researchers traced its apparent direction, the vector pointed like a perfect arrow straight back toward the Hydra cluster itself. It was as if a local whisper was wearing a distant mask. How could a signal from our atmosphere pretend to come from so far away? The answer may lie with a visitor moving at incredible speed. Picture an interstellar comet, but not a simple ball of ice. This one, forged around another star, is unusually rich in metallic dust within its nucleus. As this high-velocity object screams into our inner solar system, it plunges through Earth's upper atmosphere, the ionosphere. For a fleeting moment, its trail of ionized metal particles creates a temporary, highly reflective filament in the sky. Now, imagine the constant radio chatter of human civilization, our television broadcasts, our radar pulses constantly leaking into space. Some of this energy bounces off the ionosphere back to Earth, which is normal. But if a sliver of that human-made radio noise strikes this unique metallic comet trail at just the right angle, it could be reflected not back down, but out into deep space with its frequency signature scrambled. To a radio telescope tuned to the distant cosmos, this brief reflected glitch would appear to come from the precise direction the telescope is already pointed, in this case the Hydra cluster. The comet acts as a momentary, accidental mirror in the sky, turning our own technological echo into a phantom signal from the depths of the universe. This rare atmospheric reflection event explains both the local origin and the distant pointing. It means that sometimes the most puzzling interstellar signals are not messages from afar, but our own noise, transformed by a passing cosmic traveler into something wonderfully strange. Our own radio noise reflected back at us is a cosmic prank, but the next signal carries the weight of a fundamental law seemingly broken. It comes from the detailed chemical autopsy of another interstellar visitor, performed by one of the most powerful optical telescopes on Earth, the Very Large Telescope in Chile. Astronomers were meticulously analyzing the spectrum of light from the comet's glowing coma, breaking it down into the unique fingerprints of its chemical constituents. Amid the expected lines for common molecules like cyanogen and diatomic carbon, they found something that made them pause. It was a faint but unmistakable emission line from oxygen atoms. Not just any oxygen signal, but a so-called forbidden line. In atomic physics, forbidden lines are spectral signatures that are incredibly unlikely to occur under normal conditions. They require the atom to be in an extremely low-density environment, like the vast vacuum between stars, where it can hold a fragile, excited state for a long time without colliding with another particle and losing that energy. Alternatively, they can be produced by tremendously violent events, like the searing plasma around a black hole or within a supernova remnant. Finding such a line in the fuzzy head of a comet was deeply puzzling. A comet's coma is not a perfect vacuum. It is a cloud of gas and dust, thin by Earth standards, but still dense enough that atoms should collide constantly, quenching these delicate forbidden states before they can emit their distinctive light. So what was happening? One possibility is that this particular interstellar comet was exceptionally pristine and diffuse. Its nucleus, never warmed by a sun before, was releasing gas so slowly and into such a large volume that the inner coma became tenuous enough to mimic the deep space conditions of its origin. The forbidden line was then a direct echo of the interstellar medium itself, a whisper of the comet's long journey through the galactic void preserved in its own breath. The other possibility is more unsettling. It suggests something within the comet itself was acting as a powerful energy source. Could natural radioactivity from rare elements in its core be exciting the gas? Or perhaps complex chemical reactions on its dark, porous surface were releasing stored energy in a way we have never seen. This forbidden oxygen line is more than a spectral curiosity. It is a boundary marker. It asks us where the environment of a simple icy body ends and the exotic conditions of deep space or stellar violence begin. Is a comet just a melting snowball, or can it be, under the right circumstances, a miniature laboratory for high-energy physics? This single, faint line of light blurs those categories, suggesting our cosmic visitors may carry hidden, energetic hearts. A forbidden oxygen line whispers of hidden energies, but some signals arrive as sudden, unmistakable winks of light. Across two continents, hours apart, amateur astronomers reported something extraordinary. In rapid succession, they captured brief, brilliant optical flashes from two entirely different regions of the night sky. These were not meteors, not satellites, and not equipment glitches. The flashes were meticulously logged, and when the data was later compiled, a chilling pattern emerged. The two flashes, separated by thousands of miles and several hours, were synchronized in a very specific way. Their duration, their intensity, and the way the light faded were nearly identical. It was as if the same cosmic light switch had been flipped in two different places. The analysis pointed to a single, breathtaking explanation. Imagine a single, sizable interstellar comet, perhaps one made of unusually pure water ice, approaching the inner solar system. The sun's increasing heat creates thermal stress, and the fragile object fractures. It splits into several large fragments, each now tumbling through space independently. If those fragments have surfaces polished smooth by eons in the interstellar void, or if they contain large, flat facets of crystalline ice, they can act like mirrors. As they rotate, there will be a fleeting moment when that mirror-like surface catches the sunlight at the perfect angle to reflect a concentrated beam directly toward Earth. For a second or less, that fragment becomes a brilliant beacon. The synchronized nature of the two observed flashes suggests they came from two separate fragments of the same original body, tumbling with similar rotation periods. They flashed in unison because they were born from the same event, siblings in a cosmic breakup. Verifying such events is a monumental technological challenge. These flashes are transient, unpredictable, and require a global network of synchronized cameras constantly watching the entire sky to catch them in the act. We lack that comprehensive system, so these paired flashes remain a tantalizing, unconfirmed report. Yet they open a stunning possibility. If real, they offer a method to track the real-time disintegration of a visitor from another star, not by its dust or gas, but by the glitter of its shattering pieces. Each flash would be a death knell, a final, brilliant signal marking the end of a journey that began around an alien sun. The universe has a way of bending light to tell its secrets. In the crowded starfields toward the galactic center, a project called the Optical Gravitational Lensing Experiment, or OGLE, watches for a specific cosmic magic trick. It monitors millions of stars, waiting for them to briefly brighten. This happens when a massive object passes directly between the star and Earth, its gravity acting as a lens to magnify the distant starlight. Most of these events are clean and symmetrical, a smooth curve of brightening and fading, but one event was different. The star's light did not rise and fall in a perfect bell curve. Instead, the brightening was lopsided with a strange, jagged asymmetry in the data. The lensing object was not behaving like a single, solid body. The leading explanation for this odd signal is as beautiful as it is strange. It proposes that the object bending the light was not a lone planet or a failed star. It was a dense, compact swarm of interstellar comet nuclei, a tightly packed cloud of perhaps millions of dark, icy hearts moving together through the void. Imagine a vast, shapeless school of dark fish passing in front of a lighthouse. Each individual comet nucleus has its own tiny gravitational field. As the swarm moves across our line of sight, The combined and shifting gravity of all these countless fragments creates a complex, evolving lens. It does not bend the starlight in a single, smooth focus. It warps and distorts it chaotically, like looking through a moving, rippled pane of glass. This produces the asymmetric, jagged brightening curve that so puzzled astronomers. Mathematical models show that a swarm of low-mass objects, if they are numerous and close enough together, can perfectly replicate this signature. It is a signature that a single, large object simply cannot make. If this interpretation is correct, it would be a revolutionary discovery. It would provide the first direct evidence for vast, nomadic populations of dark comets that travel not as lonely wanderers but in immense, cohesive flocks. These swarms would constitute a form of dark, compact matter drifting unseen between the stars, detectable only when they pass in front of a distant beacon and twist its light into a telltale knot. This single, lopsided curve of light is more than a data anomaly. It is a potential window into a hidden architecture of the galaxy, where the darkness is not empty, but teeming with frozen congregations on an endless journey. Far beyond the planets, where the sun's influence finally fades into the galactic wind, our most distant robotic envoys have heard a new kind of whisper. The Voyager probes, now sailing in interstellar space, have recorded something profound. It is a low-frequency hum, a slow, pulsing radio wave that seems to echo across the boundary of our solar system. This signal is not a burst but a resonant tone, and its origin may be tied directly to the passage of an unseen interstellar traveler. The location is key. The signal was detected near the heliopause, the turbulent frontier where the outward pressure of the solar wind collides with the inward pressure of the interstellar medium. It is a chaotic, magnetic borderland. The theory is as elegant as it is dramatic. Imagine an interstellar comet wrapped in its own faint magnetic field, plunging through this violent boundary layer. As it crosses, its magnetic field slams into the concentrated magnetic field piled up at the heliopause. This interaction is not a silent merging. It is a shock, a sudden disturbance that sends ripples propagating along the boundary surface, much like a stone dropped into a pond sends out circular waves. The vast, curved surface of the heliopause itself acts as a resonating chamber, a cosmic drumhead. The impact of the comet's magnetic field strikes this drum, and the resulting vibrations are emitted as these slow, modulating radio waves that our probes can hear. The signal's frequency is telling. It is not a pure tone, but one that shifts and bends. This modulation is the fingerprint of the encounter. As the comet moves, the angle and strength of its magnetic interaction change, causing the pitch of the echo to waver. It is a direct recording of the event's dynamics, a real-time sonification of a collision at the edge of everything we know. This means we are not just looking for these visitors with light. We might also be able to listen for their distant, resonant footsteps as they breach the magnetic shore of our solar system. That deep, humming echo is the sound of our cosmic border being touched, a reminder that even in the profound silence of interstellar space, the universe finds a way to make its presence known through a vibration we can feel in our data. The deep hum at the solar system's edge is a vibration we can measure, but some signals arrive as a physical substance we can hold. Scientists have long sent specialized aircraft into the stratosphere, skimming the edge of space to collect microscopic dust that rains down from above. Most of these particles are familiar, debris from asteroids or comets born in our own solar system, but a few grains trapped on sticky collectors high above the clouds tell a different story. Their tale is written not in light or radio waves, but in the very atoms that compose them. When analyzed with extreme precision, these rare motes of dust reveal a startling signature in the ratio of two forms of carbon. Carbon comes in stable isotopes, atoms with the same chemical personality but different weights. Carbon-12 is the common, lightweight version. Carbon-13 is slightly heavier. In our solar system, from the Sun to the planets to every comet we have studied, the ratio of carbon-12 to carbon-13 falls within a predictable, narrow range. It is a fundamental fingerprint of our cosmic neighborhood. The dust collected from the stratosphere, however, broke that rule completely. The ratio was skewed dramatically, favoring the lighter carbon-12 to a degree never seen in any local object. This was not a slight variation. It was an alien composition, a chemical shout from somewhere else. The most compelling explanation is that we captured a direct sample from an interstellar comet that never announced its arrival with a bright tail. Picture a small, dark nucleus, rich in pristine carbon compounds, slipping into Earth's upper atmosphere. The friction of entry does not just make it glow, it utterly vaporizes the object in a flash of heat. The comet is gone, but its essence remains, scattered as a fine smoke of exotic dust that slowly drifts down through the stratosphere. Our high-flying collectors captured that smoke. The aberrant carbon ratio is the comet's final chemical whisper, a piece of its birth certificate from around another star. This signal is profoundly different from all the others. It is not electromagnetic. It is a tangible relic, a piece of a visitor that physically touched our world and left a part of itself behind. It transforms the mystery from something we observe at a distance to something we can literally put under a microscope. That microscopic grain, with its impossible atomic ratio, forces a humbling realization. The boundary between our world and the interstellar void is not a clean line. It is a sieve, and through it falls the ashes of messengers we never saw arrive, each carrying a coded story of an alien forge we have yet to find. Gamma rays represent the universe's most violent language. These are titanic explosions, often from colliding neutron stars or collapsing massive stars, that can outshine entire galaxies for a few fleeting seconds. But a subtle pattern has emerged from the data, a ghostly echo that defies easy explanation. Astronomers have noticed that after certain short gamma-ray bursts, the kind thought to come from neutron star mergers, follow-up observations sometimes reveal a faint, fast-moving speck in the same patch of sky, arriving centuries after the initial flash of light. The statistical link is tentative, a whisper in the noise, yet it points to a staggering chain of events. The radical idea is this: what if the gamma-ray burst itself is not the end of the story, but the beginning of a journey? Imagine a cataclysm in a distant solar system, perhaps two neutron stars spiraling together and merging. The explosion is unimaginably powerful, but it is not perfectly symmetrical. In the chaotic gravitational maelstrom, a chunk of planetary debris or a comet from that system's outer reaches could be caught in the blast wave. This icy fragment would not be vaporized. Instead, it would be hurled outward like a stone from a cosmic slingshot, accelerated to a significant fraction of the speed of light. The gamma-ray burst is the brilliant flash of the detonation, visible across the universe almost instantly. The comet, however, travels far slower. It begins a lonely voyage that may last for centuries or even millennia, a dark, frozen shard carrying the memory of that ancient violence. When it finally enters our field of view, we see it as a faint, fast-moving object, an afterthought to a cataclysm we witnessed long ago. We are not seeing the explosion itself, but a piece of shrapnel from the blast, a delayed signal carrying the forensic evidence of the event. This transforms our understanding of these interstellar visitors. They would not be mere icy nomads on a peaceful drift between stars. They would be refugees, survivors of stellar-scale apocalypses. Their very existence and incredible speed a testament to a violence that occurred before human history began. The correlation, if proven, would create a new kind of cosmic archaeology. By studying the composition of such a hypervelocity comet, we could potentially read the conditions of that long-dead stellar merger, learning about events we only saw as a brief, brilliant flash in the dark. It suggests that some of the silent wanderers passing through our neighborhood are not just travelers, but the scattered ashes of other solar systems' most dramatic endings. The deep hum of a magnetic drumhead and the ashes of stellar explosions speak of arrivals and departures, but sometimes the most profound signal is one of absence. It is a pattern etched into the very fabric of our solar system's outer darkness. Astronomers studying the most distant comets, those with orbits lasting thousands of years, have noticed something deeply strange. A specific group of these icy objects from the vast reservoir we call the Oort cloud do not follow random paths. Instead, their incredibly long elliptical orbits seem to be synchronized. Their orbital periods, the time it takes to complete one long journey around the Sun, fall into a subtle mathematical harmony. They are in resonance with an unseen force. This is the signal of a ghostly conductor. Think of it like this: a child on a swing moves back and forth with a natural rhythm. If you give them a small, perfectly timed push at the peak of each swing, you can make them go much higher with very little effort. That perfect timing is a resonance. Now imagine that instead of a person pushing, there is a massive invisible hand that gave one colossal shove 10,000 years ago. The swing, or in this case a comet, is still feeling the effects of that ancient push, its orbit forever locked into that timing. For our distant comets, the mathematics point to a single, terrifying possibility. The conductor, the source of that resonant push, is not here anymore. It was a giant interstellar comet, a behemoth perhaps dozens of miles across, that barreled through our outer solar system in the distant past. It did not collide with anything. It did not break apart. It simply passed by, a dark, frozen mountain moving at interstellar speeds. As it sailed through the sparse sea of our own native comets in the Oort cloud, its immense gravity acted like a sweeping tide. It did not capture these comets or fling them away. Instead, it orchestrated them. For the comets that happened to be at just the right distance and moving in just the right direction, the giant's gravity gave them that perfectly timed gravitational nudge. It tuned them, locking their orbits into a lasting harmonic relationship with its own long-vanished trajectory. The giant itself is gone, lost back to the interstellar dark from whence it came. But its influence remains, frozen in the celestial mechanics of the objects it left behind. The resonant pattern we see today in our own comets is the lingering wake of that passage, like the organized ripples on a pond long after a stone has sunk. We are not detecting the object itself. We are reading the fossilized imprint of its gravity, a signature written in the slow dance of icy bodies that takes millennia to complete a single step. This signal asks us to listen to the silence and hear the echo of a giant that passed in the night, still conducting its symphony from an empty podium. Deep beneath the Antarctic ice, another kind of whisper is being hunted. The Ice Cube Neutrino Observatory is not a telescope of glass and mirrors, but a colossal cubic kilometer of pristine ice, embedded with thousands of sensitive light detectors. It waits in the eternal dark for the most elusive particles in the universe, neutrinos. These ghostly travelers, born in the hearts of stars and cataclysms, pass through planets as if they were empty space. Only very rarely does one interact with the ice, producing a faint flash of light that Ice Cube can capture. In the relentless stream of data, researchers once noted a subtle anomaly. Over a period of several weeks, there was a faint but statistically curious uptick in neutrino detections. These events did not point back to a known source like a blazar or a supernova remnant. They seem to come from a diffuse region of space within our own solar system, a direction with no obvious violent engine. The signal was too weak to declare a discovery, but too persistent to ignore. It was a phantom in the machine. The explanation, if true, is a masterpiece of cosmic subtlety. It begins with a specific kind of interstellar comet. This one is not just made of water, ice, and dust. Locked within its frozen heart are significant quantities of radioactive isotopes, particularly one called aluminum-26. This isotope is unstable. Over time, its atoms decay, transforming into magnesium and releasing energy in the process. This decay is not a violent explosion. It is a slow, steady simmer of radioactivity that gently heats the comet from within. Crucially, this nuclear process also produces a faint, steady stream of neutrinos as a byproduct. Normally, the neutrino flux from a single small object like a comet would be utterly undetectable against the background roar of the cosmos, but here is the key. This hypothetical comet was not at its distant home. It was passing directly through our inner solar system, bringing its radioactive heart relatively close to Earth. For those few weeks, our planet was swimming inside the comet's extremely faint neutrino halo. IceCube, the most sensitive neutrino detector ever built, might have just barely registered that subtle increase in the ghostly rain. This blurs the line between astronomy and particle physics in a fascinating way. We are no longer just looking at the comet's reflected light or its radio emissions. We are detecting the nuclear furnace in its core, the slow ticking of its atomic clock. The signal is not about the comet's surface or its journey, but about its very composition and the hidden energy that has been powering its chemistry for millions of years. Interpreting such a signal is a monumental challenge. It requires untangling a handful of extra neutrino events from the vast statistical noise of atmospheric neutrinos and distant astrophysical sources. It is like trying to hear a single specific instrument tuning its note within the roar of a full orchestra from a mile away. Yet the possibility remains breathtaking. It suggests that our most advanced particle detectors could, in principle, sniff out the radioactive breath of a silent, dark wanderer passing through our neighborhood, turning a chunk of ice and rock into a beacon of nuclear physics visible only in the most ghostly of lights. Our sun breathes a constant supersonic wind of charged particles, a river of plasma that shapes the entire solar system. Its flow is not perfectly smooth, but it follows predictable patterns. Yet on one specific day, the Solar and Heliospheric Observatory satellite, watching the sun from its quiet perch in space, recorded something that broke the pattern. The solar wind measured at Earth's orbit suddenly shifted. Its direction veered and its density spiked in a sharp, localized pulse. For a few hours, it was as if the entire river had hit an invisible rock and been forced to bend. The official explanation pointed to a coronal mass ejection, a belch of magnetized plasma from the sun itself, but the timing was off and the geometry was strange. The disturbance appeared not as a wave spreading from the sun, but as a distinct moving pressure front within the wind itself. This opened the door to a far more intriguing culprit. Imagine not a solar event but an intruder. A large interstellar comet, one with a surprisingly strong magnetic field frozen into its icy heart, plunges through the inner solar system. As it moves, this field creates a miniature magnetosphere around the comet, a protective bubble that pushes against the oncoming solar wind. For most small comets, this effect is negligible, lost in the noise. But for a giant, magnetically active visitor, the interaction could be profound. Its mini magnetosphere would act like a plow moving through water, piling up the solar wind ahead of it and creating a turbulent wake behind. The SOHO satellite, sitting at a fixed point, would have recorded this as a sudden, sharp change in wind direction and density as that magnetic plow passed through its measurement zone. It would be a brief, localized shove against the sun's omnipotent outflow. This signal is compelling because it is so physical. We are not interpreting light or chemical signatures. We are measuring a direct, kinetic interaction, a shoving match between the sun's wind and the magnetic field of a passerby. The comet itself might have been too dark or too distant for our optical telescopes to spot, but its magnetic shadow left a dent in the solar wind that our instruments felt. This transforms a routine solar observation into a potential detective story. It suggests that some of the most massive interstellar travelers might not announce themselves with a brilliant tale, but with a silent, magnetic push against the very fabric of our solar environment. We must learn to read the ripples in the solar wind not just as weather from our star, but as the wake of unseen giants moving through our home. The solar wind's sudden bend was a silent event felt only by our machine. But 2,000 years ago, a signal arrived that was witnessed by the entire world. It was recorded not in data, but in scripture and legend. The Star of Bethlehem, that celestial guide of the Nativity story, has been debated for centuries. Astronomers have proposed planetary conjunctions, a bright supernova, or even a rare triple alignment. Yet one explanation fits the ancient descriptions with an uncanny, almost perfect alignment. It suggests the star was not a star at all, but a brilliant interstellar comet making an astonishingly close pass to Earth. The Gospel of Matthew provides the clues. It describes a star that appeared in the east, which the Magi, wise men skilled in watching the heavens, recognized as significant. This star then moved ahead of them, traveling from Jerusalem south to Bethlehem, and finally it stopped, standing over the place where the child lay. A fixed star or a distant supernova cannot move in this way against the backdrop of the sky, nor can it appear to stop and hover. A planet's retrograde motion could create a stopping point, but not the described journey across the local sky. A comet, however, does all of this. A bright comet, especially one from interstellar space on a unique hyperbolic trajectory, would first appear as a new point of light. Its position against the fixed stars would change noticeably from night to night, appearing to travel. Most critically, as it made its closest approach to Earth, its apparent motion across our sky would slow dramatically, and from the perspective of travelers on the ground, it could appear to stand still in the heavens, hovering over a specific location. The duration of the phenomenon also matches. The Magi's journey likely took weeks or months, and a great comet can remain brilliantly visible for that exact span of time, unlike a conjunction which lasts days or a supernova which fades slowly over years. The psychological impact seals the theory. To ancient sky watchers, a comet was a profound omen, a divine messenger. A standard periodic comet from our own Oort cloud might be seen as a portent, but an interstellar visitor, one never before seen in human history, blazing with unprecedented brilliance on a strange path, would have been interpreted as a world-altering sign. This transforms the Star of Bethlehem from a theological symbol into a potential historical astronomical event. It would be the oldest, most vividly documented signal of an interstellar visitor in all of human history, a comet from another star that didn't just whisper to our instruments, but blazed across our cultural consciousness, guiding the narrative of civilization itself. 2 millennia ago, a comet's light may have rewritten human history, but in the modern era, our machines capture whispers of a different kind. A radio telescope, tuned to listen for the faintest cosmic static, once recorded a signal that sounded almost engineered. It was a decametric sweep, a clean, rising tone that moved steadily up the radio band over several minutes, like the sweeping beam of a distant radar installation. The immediate assumption was terrestrial interference, a satellite or aircraft beacon, yet every check came up empty. No known satellite matched the timing or the precise, smooth frequency glide. The signal was coming from a patch of empty sky, and its behavior was too perfect, too orderly to be random noise. This left astronomers with a fascinating natural candidate, one that bridges the chaotic and the coherent. Picture an interstellar comet, this one with an unusually active and structured plasma tail. As the comet journeys through the solar system, its nucleus rotates, and its long ion tail, a river of charged particles blown by the solar wind, does not simply stream out in a straight line. It can become twisted by magnetic fields, kinked and braided like a rope of glowing plasma. Now imagine this complex, rotating structure interacting with the solar wind itself. The charged particles in the wind striking this dynamic plasma rope can generate radio emissions. It is a natural process, but the geometry introduces order. As the comet spins, the effective length and orientation of the plasma structure acting as an antenna changes. This alters the frequency of the radio waves it naturally emits. If the rotation is smooth and stable, the frequency shift would be equally smooth, creating that precise, sweeping tone across the radio band. It is a natural signal wearing the mask of a synthetic one. The universe, in this case, is not broadcasting a message. It is simply a spinning, ionized cloud in a magnetic river, and the physics of that interaction produces a byproduct that happens to sound eerily like a search pattern. This sweep forces us to refine our definitions. We often think of a technosignature as something with complex modulation, with pulses and patterns that carry information. But what if the first clue is not complexity, but a simple, pure tone that is too clean, too regular to arise from the turbulent processes we typically observe? The decametric sweep stands as a benchmark. It teaches our algorithms that nature can produce signals of stunning regularity, and that the line between a natural plasma whistle and an artificial beacon can be vanishingly thin. The next time our telescopes hear a rising tone from the dark, we will have to listen very carefully, knowing it could be the song of a tumbling comet or something else entirely. That eerie, rising radio sweep shows how nature can mimic a machine, but our final signal is the most profound of all because we cannot see it, hear it, or touch it directly. We can only feel its ghostly pull. This whisper is written in gravity itself, far beyond Neptune, in the frozen depths of our solar system. A handful of strange objects called sedenoids trace bizarre, looping orbits. They come nowhere near the giant planets, yet their paths are clustered and tilted in ways that gravity from the known planets cannot explain. It is as if an invisible hand is gently herding them. The leading hypothesis for this orbital anomaly is a hypothetical planet 9, a super-Earth lurking in the dark, but there is another, equally staggering possibility. What if the Shepherd is not a planet, but a captured interstellar dark comet of immense size? We are not talking about a mountain of ice. We are talking about a world-sized relic, perhaps dozens of miles across, composed almost entirely of exotic primordial matter. One candidate is a so-called dark comet, an object so old and depleted that it reflects almost no light, a black iceberg. Another, even more extreme candidate is a microscopic primordial black hole, a remnant of the Big Bang itself, cloaked in a thick, captured envelope of interstellar ice, a black hole wearing a frozen coat. Either of these objects would possess tremendous mass condensed into a relatively small, dark package. Its gravity would be potent enough to tug on the sedenoids over millennia, sculpting their orbits into the strange patterns we see. Yet it would emit no light, no heat, no radio waves we could detect. Its only signal would be that subtle, persistent gravitational nudge on other bodies. This idea transforms the mystery from an astronomical puzzle into a cosmological revelation. If such an object is truly orbiting our sun, captured eons ago from the interstellar drift, it would be more than just another visitor. It could be a direct sample of the universe's missing mass, a piece of the dark matter puzzle hiding in our own celestial backyard. We have spent decades building immense detectors deep underground, trying to catch a fleeting glimpse of dark matter particles. Yet the answer to part of that mystery might not be a swarm of invisible particles, but a singular, frozen monolith silently circling our sun, its presence betrayed only by the crooked paths of distant ice dwarfs. The search is now a cosmic detective story. Astronomers are scouring the infrared and optical surveys for any faint thermal glow or fleeting occultation that might pinpoint this phantom. Every unexplained gravitational wiggle in the outer solar system is a potential clue. This final signal brings our journey full circle. We began with Oumuamua's strange acceleration, a whisper of something unseen. We end with the possibility that the greatest unseen thing of all, a fragment of the cosmos's hidden mass, might not be far away in the halo of the galaxy. It might be here, a permanent dark guest in our own solar family, its silent gravity the only hello it will ever offer. The profound silence we have catalogued speaks louder than any radio burst. It brings us face to face with one of cosmology's most chilling ideas, known as the Great Filter. The physicist Enrico Fermi once posed a simple, devastating question. If the universe is so vast and old, where is everybody? The Great Filter is the proposed answer, a hypothetical barrier so immense that it prevents life from advancing to the stage of interstellar communication or travel. It could be a rare, catastrophic step in evolution. Perhaps the jump from single-celled to multicellular life is almost impossible. Or it could lie ahead of us, a future calamity like self-destruction through technology that every civilization ultimately faces. Our interstellar comets cast this philosophical puzzle in a new, tangible light. We now know these objects can be rich in complex organic molecules, the very building blocks of life. They are cosmic couriers, potentially seeding primordial oceans across the galaxy. If life's ingredients are so common, carried on these frozen ships, then the first part of the filter, the origin of life itself, might not be so great. Life could spark easily wherever conditions are right. This makes the subsequent silence even more profound. The filter then must be somewhere else. It might be the staggering fragility of biological complexity. Perhaps life routinely emerges on worlds, only to be sterilized by gamma-ray bursts or supernova before it can invent a radio telescope. The comets themselves could be agents of this filter, their impacts delivering not the seeds of life, but periodic global resets that wipe the slate clean. Or the filter could be one of consciousness and choice. What if intelligence does evolve, looks out at the silent, dark universe and makes a deliberate decision? It might choose to stay quiet, to hide. This concept, known as the zoo hypothesis, suggests advanced civilizations could be observing us, but under a strict protocol of non-interference. Our frantic scanning for radio signals from comets and stars would then be the equivalent of a child in a vast library, shouting to see if anyone else is there, not realizing the librarians are watching silently from the upper balconies, waiting for us to mature. Our search for signals within these icy messengers takes on a new dual meaning. We are not just looking for a hello, we are testing the boundaries of the filter itself. Every silent comet, every natural-looking signal is a data point. Does it mean we are alone in this galactic neighborhood, that the filter lies ahead and we have yet to hit it? Or does it mean we are surrounded by civilizations that have chosen invisibility, and the greatest signal of all is the quiet they have mastered? The comets do not answer, but their whispered secrets force us to ask the question with a new urgency. Silence may be the loudest answer, but what if the message was never meant to be a signal at all? What if it is a passenger? This brings us to one of the most profound roles an interstellar comet could play, that of a cosmic ark. The panspermia hypothesis suggests life itself could travel between the stars, not as radio waves, but as resilient microbial stowaways embedded within the protective ice of these wandering bodies. An interstellar comet is not merely a transmitter of strange energies. It is a potential lifeboat frozen in time and drifting on galactic currents for millions of years. Its dark, shielded interior could protect dormant bacteria or even more complex organic spores from the harsh radiation of space, allowing them to survive an epic journey from one star system to another. In this view, every icy visitor is a potential gardener, and the seeds of biology could be a universal phenomenon sown across the galaxy by silent, frozen ships. This is not just speculation, it is the driving force behind a new generation of mission concepts. One of the most ambitious is known as the Tampopo mission, a plan conceived by Japanese researchers. The idea is to deploy a fleet of ultralight, dust-collecting panels into the path of a high-speed interstellar comet. As the comet speeds by, its coma of gas and dust would pepper these panels, depositing pristine samples of its material. A return capsule would then bring these precious grains back to Earth for analysis in our most sophisticated laboratories. The goal is not to listen for a radio signal, but to perform the ultimate chemical and biological autopsy, searching for the building blocks of life frozen in time. The most telling discovery would not be finding simple organic molecules, which we already know exist in space. The true revolution would come from detecting amino acids with a specific chirality. Amino acids are the Lego blocks of proteins, essential for life as we know it. They come in two mirror image forms like left and right hands. Non-biological processes produce a 50-50 mix of both types. Life on Earth, however, uses almost exclusively the left-handed form. This uniformity is a signature of biology, a fingerprint of a living process. If we were to catch material from an interstellar comet and find within it an abundance of either left or right-handed amino acids, the implications would be universe-shattering. It would be strong evidence that the process of life, or at least its chemical preference, did not begin here. It would mean the chiral selection, that first decisive step toward biology, happened somewhere else around another star and was delivered to us. That single microscopic detail in a speck of dust would be the ultimate biological signal, rewriting our origin story from a local event on a watery planet to a galactic inheritance. We would no longer be just inhabitants of Earth, but potentially the descendants of travelers who arrived on a comet's whisper, changing forever our understanding of our place in the cosmic story. The search for whispers in the dark is about to become a symphony. Our tools are evolving from simple listening posts into a galactic nervous system, poised to catch every faint murmur and fleeting shadow. The Vera C. Rubin Observatory, currently rising from a Chilean mountaintop, will soon begin the legacy survey of space and time. Its immense mirror and gargantuan camera will scan the entire visible sky every few nights, not for years, but for an entire decade. It will not just find the occasional bright interstellar visitor, it will catalog them by the thousands. This relentless, all-seeing eye will catch the subtle, dark wanderers that have slipped past us, mapping their silent trajectories with statistical power we can barely fathom. We will move from rare anecdotes to a true census, learning for the first time just how crowded the interstellar highway really is. Simultaneously, the square-kilometer array, or SCAR, will begin listening. This colossal network of radio antennas spread across 2 continents will be the most sensitive ear ever turned to the cosmos. It will not just listen for the loud, obvious bursts. It will detect the faintest radio whispers from cometary plasma, the subtle crackle of magnetic interactions at the edge of our solar system, and the quietest hum of a distant swarm. Its power lies in combining signals from thousands of dishes, creating a virtual telescope so vast it could detect a mobile phone signal on Jupiter. With the SKA, the decametric sweeps and sporadic pulses we now struggle to hear will become clear, distinct voices, their structures laid bare for analysis in real time. But perhaps the most thrilling frontier is not just observation but interception. For the first time in history, mission concepts are being seriously drafted not for planets or asteroids, but for a moving target from another star. The next time an object like Oumuamua is discovered on its inbound trajectory, we could be ready. Projects like the European Space Agency's Comet Interceptor mission have already proven the concept of a rapid response spacecraft parked in a holding orbit waiting for the right target. The next step is an interstellar interceptor. Imagine a small, agile probe equipped with a high-resolution camera, a mass spectrometer, and a dust collector, launched on a powerful rocket to chase down the visitor. It would fly alongside the dark nucleus for weeks or months, mapping its surface, sniffing its outgassing, and perhaps even deploying an impactor to sample the material beneath its crust. We would go from distant spectators to close companions, reading the comet's story not from the faint light it reflects, but from the physical reality of its ancient alien surface. This convergence of all-seeing surveys, hypersensitive listening, and potential rendezvous marks a fundamental shift. We are no longer waiting for the universe to send us a postcard. We are building a global network to read its entire mailbag and drafting blueprints to send a return address. The golden age of decoding these cosmic signals is not a distant promise. It is dawning with the next night's observation. The dark is about to get a lot less quiet, and the next whisper we hear might be one we can finally answer. From the faintest infrared warmth of distant swarms to the violent flash of a pulsar's searchlight, the catalogue of whispers is breathtaking. We have listened to radio sweeps that mimic machinery, felt the magnetic shove of a dark giant in the solar wind, and even caught the atomic signature of alien carbon in high-flying dust. These are not merely 25 isolated puzzles. They are facets of a single, monumental revelation. Interstellar comets are far more than simple icy nomads. They are cosmic Rosetta Stones, each one a condensed archive from another star. A single dark nucleus can carry a chemical message in its ices, broadcast a plasma whisper in the radio, cast a gravitational shadow that herds other worlds, and leave a physical sample as its final testament. Its surface, its rotation, its fragmentation, and its death all become different languages telling the same story of origin and journey. The message is not one of greeting, but of existence. It is the universe showing us its raw, unedited diversity, proving that the ingredients for wonder, and perhaps for life itself, are being endlessly mixed and shipped across the galactic expanse. So the next time you find yourself beneath a clear night sky, take a moment to look up into that deep, starry silence. Remember that the darkness is not empty. It is a highway, a nursery, and a gallery of frozen history. The next great mystery is not waiting in some distant galaxy. It could be hurtling toward our solar system right now, a silent, dark speck against the infinite backdrop carrying a multitude of whispers. All it needs is for us to be listening.